Hi everyone, welcome to our first lecture on linear motion. In linear motion we'll be covering both horizontal linear motion and vertical linear motion, but today's lecture will begin with the idea of horizontal linear motion. Now before we get started we have to understand some terms. Some terms that we're used to using in everyday life, and then there's sort of physics counterpart and what they mean. So to begin with, we have to look at the idea of the term distance versus something called displacement. Distance is a scalar value, meaning it simply has magnitude and amount, and basically just tells you how far you've gone. So, for example, if I were to tell you to go up to the track and get at the starting line and run down to the 100-meter finish point, turn around, and run back, well then the total distance that you have covered is 200 meters, because that's basically how far you've gone. Displacement, however, is a vector, meaning it has both magnitude and direction. And is defined as your distance relative to a specific point. So if we look at that same example, get on the starting line, run 100 meters, turn around, and run back where you started. Your displacement is 0. And the reason it's 0 is because how far you are relative to your starting point is 0. You're right back where you started. So displacement has to do with how far you are from where you began to where you ended. Now, the symbol we use for displacement is the letter x, typically. Now, displacement can come in a lot of other letters. H for height, R for radius, various things like that, but x is the most common one. And the standard unit of displacement is the meter. Now again, the interesting thing about this displacement factor versus distance. Now again, even though you ran 100 meters down and 100 meters back, you did travel 200 meters in total distance, but you basically went nowhere. And in fact, you could start on that same starting line and go and start running around the track many times, maybe out along the fields, all around, all over the place, loop around a few times, and come right back to where you started, and your displacement is still 0. You've gone nowhere. And again, that's the big difference between displacement and distance. Despite all that distance you traveled, you've gone nowhere in terms of displacement. Now, since displacement is a vector, it can be a positive or negative value. Okay? Distance is usually solely a positive value, but displacement can be a positive or negative value. Now, you have to be careful about that. One of the things you have to be careful with the idea of vectors and dealing with that in physics is that if your math teacher were to put two numbers up for you and say, put this number and this number, and said, which one was bigger? Well, the natural answer would be, of course, 2. And that's wrong. It's actually -4. Now I know your math teacher said that positive numbers are always bigger than negative numbers, but when you talk about the term displacement, if this is sort of your starting line and one person is standing 2 meters from here, and the other person is standing 4 meters from here. Well, the person 4 meters away is always going to be a greater displacement than the person that is 2 meters away. But in terms of physics, because this line right here, is our sort of reference point, this direction might be considered a negative direction, while this direction is a positive direction, meaning the person on the left's displacement is -4 meters related to that line, while the person on the right is +2 meters. Now again, 4 is always bigger than 2. So the person with the displacement of -4 meters has a greater displacement. So be careful of those vector signs. The next set of terms we're going to look at is the idea of something called speed versus in physics something called velocity. Speed is a scalar value, basically telling you how fast you're going. Velocity, however, is a vector value and is defined as a change in displacement over time. The symbol we use for velocity is a lowercase v, and its standard unit is the meter per second. Now, let's take a look at that. Let's say, again, I send you back up to the track, and I tell you to run at 100 meters, turn around and run back, and let's say it takes you 20 seconds to do that. Now, aside from the fact that you probably should be training for the Olympics, because that's really fast, how would you determine what your speed is? Well, if we kind of look at this, we could say, well, I went a distance of 200 meters in a time of 20 seconds. So if I have a distance of 200 meters and a time of 20 seconds, well, if I divide those two, I get meters per second. Okay, so let's do that. And that gives me 10 meters per second. Now, the tricky part about that number is when were you traveling 10 meters per second? Were you doing that the whole time? Were you doing it at the beginning, at the end? It's very difficult to actually say what your speed was, because really this isn't a way to determine speed. It's something called your average speed. Your average speed is found by your total distance over your total time, and that's basically what we just did. So this 10 meters per second could be said to be an average. Doesn't mean you went 10 the whole time, it just sort of averaged out that way. Now the problem with that is it doesn't really tell much in terms of details of what you're doing. So let's look at that term velocity. Again, we'll look at the same idea. 100 meters down, run back, time of 20 seconds. Okay. Now, the way we define the term velocity is called the change in displacement over time. Now, let me show you a quick thing about math and physics. We use this symbol, which is looks like a triangle, but is actually the Greek letter delta. Anytime you see a delta, that means change in. Or, basically, when you see a delta, it says to subtract whatever your final value is minus whatever your initial value is. So if I were to define velocity as a change in displacement over time, well, the symbol for displacement is an x, so I'd have delta x over time. So if I was to sort of write this out, okay, write out that delta, well, that would be my final displacement minus my initial displacement all over time. Now, by the way, a couple things about my writing. One, you'll notice that my v for velocity has that little tail on it. There's two reasons. The letter v pops up several times in physics throughout the year, and so I do velocity to look like that to always know that that's velocity v. And the other reason is that's what my high school physics teacher taught me to do, so I still do the same thing. Then when we talk about final and initial terms, well, I use a subscript f anytime we have a final term, but I use the subscript o for originating. In other words, that your initial term, I use the subscript o. Now, here's the problem with trying to do velocity this way. Because as we learned before, if I start at the starting line, run 100 meters down and back, my final position and my initial position are the same. In other words, my velocity is 0. Again, despite all that running, I appear to have done nothing. So is that really any better than average speed? No, not really. And that's one of the difficult things to try to use averages, because in a way, even this way of doing velocity is a bit of an average. So, in physics, we're going to look at something very different. We're going to focus more on something called an instantaneous velocity. In other words, your velocity at any given moment. So we'll pick very specific time points and analyze what our velocity is at that particular time. It'll make more sense as we move along here later on. Now, because velocity is a vector, it also can be positive or negative. And again, it all depends on the idea of direction. Now, before, if we sort of had a reference line and we said, if you're standing on this side of it, that's the negative side. If you're standing on the other side, that's the positive side. Okay? But velocity has to do with which direction you're actually traveling. So for example, I could be running to the left, even though I'm standing on the right, and that is a negative velocity because I am moving in the negative direction. Equally, I could be running this way, and no matter where I am, that's a positive velocity because I am traveling physically in what I've called the positive direction. So where displacement depends on where you are, velocity depends on where you're going. Now, a particular type of velocity that is important in physics is something called a constant velocity. Now, the word sort of defines itself. It simply means that a velocity that is not changing, that is steady over the whole time. So let's look at that instead of just number forms, because if I have a constant velocity of 5 meters per second, it just means I'm going 5 meters per second everywhere I go. Let's look at it in terms of some graphs. So for example, let's say I wanted to show something traveling on a velocity time graph that was traveling at a constant velocity. Now, some people might think, oh, I'll just draw a line that looks like that. But remember, this is a velocity graph. So if the line is going up, that says my velocity is increasing as time is going along. So that can't be right. So a constant velocity on a velocity time graph would look like that, okay, at whatever value we're traveling. So if I was traveling at 5 meters per second, that constant velocity would say that for however much time I'm traveling steadily at 5. Of course, if I had a negative constant velocity, I would have to draw it below the axis, and that would be, let's say, a negative constant velocity. Now, on a displacement graph, though, again, if my velocity is constant, okay, and remember, velocity is measured in the units of meters per second. Well, if my velocity is constant, that means I'm gaining the same number of meters every second. That would be this line. Okay, something that has a constant slope on a displacement time graph would indicate that it has a constant velocity. Now, here though, it doesn't always matter so much where that line is, it matters what the slope of that line is. For example, if I have a line that looks like this, even though it crosses the axis, it's still a constant velocity. And in fact, it's actually a constant negative velocity because the slope is in the negative direction versus the other one that is a constant positive velocity because the slope is always positive. Note, you also don't have to always start at 0. At the time that you're measuring, you may already be in motion, may have some velocity at that particular point. Now, that slope seems to be the key word. So again, if I'm looking at another displacement time graph, and let's say I have 3 different lines. Line A, line B, and line C. All of them are constant velocities. Now, if my question was, which one of these is traveling fastest? You might be tempted to think, oh, it's A, because A clearly has a steeper slope than B and is in the positive direction. But now remember, velocity is a vector, okay, meaning that when you ask about which one is going faster, that's magnitude, not necessarily direction. Now, line C here has the steepest slope. So even though it's in the negative direction, since it has the steepest slope, it must be traveling the fastest. So line C would have the highest velocity, and of course line B would have the lowest velocity, and A would be sort of somewhere in the middle. So the steepness of the slope on a displacement time graph tells you basically how fast or how slow the constant velocity is. The last term is acceleration. Now there's no vector scalar difference. Acceleration is only a vector. It always has some sort of direction. Acceleration is what makes physics difficult. If nothing accelerated, this would be a really, really easy class. But of course, if nothing accelerated, there really wouldn't be much of a universe anyway, so kind of stuck with it. We define acceleration as a change in velocity over time. And the symbol for acceleration is conveniently lowercase a, but its units are the meter per second squared, sometimes called the meter per second, but it's actually the meter per second squared. So if we were to write that out, acceleration would be delta v, change in velocity, over time. Or expanding that out, your final velocity minus your initial velocity, all divided by time. Again, change being final minus initial. So again, acceleration, change in velocity over time, final velocity minus initial velocity, all over time. Now, since acceleration is a vector, it can be positive or negative. But it can be tricky. It's a very, very tricky thing because most people think, okay, if I have a positive acceleration, it must mean I'm speeding up. If I have a negative acceleration, it must mean I'm slowing down. That's not always true. Now again, we talked about sort of that reference line, and this way we're calling negative, this way we're calling positive. Again, if I'm standing to the left of that line, then I have a negative displacement. If I'm standing to the right of that line, then I have a positive displacement. That's easy enough to understand. If I'm traveling to the left, I have a negative velocity, no matter where I am. If I'm traveling to the right, I have a positive velocity, no matter where I am. Again, it's that acceleration part that can be tricky. See, it's possible to be traveling to the right and have a negative acceleration. Now, most people would say, well, that's easy enough. That simply means I'm slowing down. And that's true. But it's also possible to be traveling to the left and have a negative acceleration. And you're not slowing down. You're actually speeding up. And the reason why is because if I'm traveling in the negative direction and I'm accelerating that way, that means I'm increasing my velocity in the negative direction. So that means I have actually a negative acceleration. So acceleration is going to be a very, very tricky thing to think about, especially when it comes to vectors. Now, what if we had a constant linear velocity? Well, again, if the idea of a constant velocity is a velocity that does not change, then whatever my final velocity is must be the same as whatever my initial velocity is. Therefore, there can be no change in velocity. So, if I have a constant linear velocity, my acceleration is always zero. That is a very, very important concept. constant linear velocity, acceleration is zero. Very, very important concept in physics. Okay, so that's our introduction here to the idea of the terms that we're going to deal with linear motion. See you next time.